which is what do we mean when we say integers modulo n? What do we mean by a zero divisor? And what do we mean by a graph, at least in the case of my presentation. So first of all, integers modulo n. You see this weird looking capital letter Z. This is how we denote integers. And integers are basically, -3, -4, -2, 0, 1, 2, 3. So they're whole numbers, but with negative and 0, and so on. So that's how we denote them, with this odd looking Z. Now, let's say, in mathematics, when we say like, oh, just any number, we choose a letter for it. For in this case, let n be some integer greater than 1. So we say what this means is that let's choose some number, we call it n, and it's, greater than 1. It could be 2, 3, 4, 5, and so on. Then we denote integers modulo n as z subscript n, as you see over here, as a set, or like, a group of number, a set of numbers that goes from 0 to n minus 1. So 0, 1, 2, so on until we reach n minus 1. Also, this is the reason why we, integers modulo n are very interesting, is because let's go back to perhaps 4th grade, 3rd grade. You remember when you used to divide two numbers, sometimes you get a remainder. So dividing any integer by a number n results in some element in Zn. This is another way of saying that Zn is the set of all possible remainders if you bring any number and divide it by n. So for example, let's look at Z5. Z5 goes from 0 to 4, right? 0, 1, 2, 3, 4. And let's traditionally, the way we learned elementary school, divide 88 by 5. We'd get 17, remainder 3. Or in another way that we could say it is, this is congruent to 3 mod 5. 88 is congruent to 3 mod 5. I made a mistake over here. I apologize. What that means is when they say 88 is congruent to 3 mod 5, is that if we divide it by 5, we'll get a remainder of 3. Now, zero divisors, at least in the context of integers modulo n. Now, a bit of a warning, zero divisors is a much larger term that encompasses something in math we call rings. But in this case, we're only focusing on Zn, which is also a ring, but there is no need for today's presentation to go into that. So we say a number a is a zero divisor in Zn if there exists another number, we call it b, also in Zn, such that ab is equal to some multiple of n. So instead of saying multiple, I just wrote m, some multiple of n, which is congruent to 0 mod n. So if we divide it by n, we took the remainder we get is 0, where m is any positive integer. Now, in this project, we ignore 0 in Zn as a zero divisor. In literature, there's a lot of reasons for it, but it's just for the sake of simplicity, because once I show you the graph, it will complicate things. It's a trivial case. We don't really care, because anything multiplied by 0, you get 0. So here are some examples. For example, this set 2, 3, and 4 are zero divisors of 6. Now, if you take any number in the set and you divide it, there has to exist another number in the set that if you multiply them by each other, you get 6 or a multiple of 6. And we can see that, 4 times 3, you get 12. But keep in mind, it doesn't mean that all numbers in the set. For example, if we take 2 times 4, that's not a multiple of 6. What this just says is that, within the set itself, there exists some other number. And sometimes the number is itself. Now, let's go for Z25. Again, the zero divisor of Z25 is 5, 10, 15, and 20. Now, some of you might notice something, that 25 is 5 squared, and all of these are multiples of 5. We'll get to that later. And if you have noticed this, that's a very good observation. In fact, my whole project is based on this. Let's go for the Z15. Zero divisor 3, 5, 6, 9. And again, if someone has noticed, 15 is 3 times 5, and the set is all multiples of 3 and 5 less than 15. Now, finally, there's something that I need to really focus on, is that there are no zero divisors for Z11. In fact, if you take any prime number, there are no zero divisors for its, Z, for mod prime. The reason behind that is, by definition, a prime number is only divisible by itself and one. So there are no two numbers less than the prime, such that if you multiply them by each other, you'd get the prime number or the multiple of the prime. Now, graph. So the main first two things you need to know about a graph is that a graph consists of vertices and edges. Vertices are these nodes that you see, and the edges are the lines between them. That is, if there is a line. You could have a completely unconnected graph where there exists no edge whatsoever. Now, when do we put an edge between two vertices? Depending on the type of the graph you're doing, you can set any condition for like when to put an edge and when not to put an edge. Now, a path in a graph denoted by capital P is of length m. So, there's something called a path that has some length, we call it m, is when you have m plus one distinct vertices, as in n plus one of these like little dots, and there is a dot, and there's a way between the first vertex to the last vertex such that it doesn't cross a vertex twice. So let's say for example, let's take for example 18 and 5. So the path between 18 and 5 is 18 to 10 to 4 to 5, or it could be 18 to 10. There are multiple paths in this case. So that's the path. And the length of the path is, m plus 1, but in a more colloquial term, in a more, as Professor M will call, straight language. For example, if we take 18 to 5, it's how many edges are between them, how many lines are between them. Then we have a cycle. A cycle of a graph of length m is a path from a vertex to f, such that, we take v1, v2, and so on. Then it goes to Vm, but Vm again goes back to V1, where again all of these vertices are distinct. So it's a path where it cannot cross the same vertex twice. If we go to the graph that I showed you, a good example of a cycle, for example, would be 4 to 5 to 12 to 15 to 4, and that's because it has it has four edges, so it's a cycle of length 4. Now we can get to what my research, my paper is about. So, introduction. Let ZGN be an undirected simple graph, and what we mean by undirected, that is, well, I'll have to refer to this a lot. That you see these edges, they don't have a direction, so to speak. They're not like an arrow showing up or down. They're undirected. And simple means that each vertex can at max have one edge. It either has no edge or two vertices can only have at max one edge between them. And each vertex cannot have a loop. That means that it cannot have a vertex, directly. It cannot have an edge directly referring to itself. So that's what we mean by undirected simple graph. Now we let Vn is the set of vertices in ZGN, with elements being the zero divisors, again, except for 0 of Zn. So we take all the zero divisors of Zn and we put them in, they're now called Vn, and each one of them is a vertex in the graph. And when are two vertices, when do they have an edge, or when are they adjacent, in other words? That is if and only if A times B, A and B being two vertices in Vn, are congruent to 0 mod n. That means their multiplication is equal to n, or a multiple of n. So now let's go to the concept of bipartite graph. Strictly speaking, the graph is bipartite if V, which is the set of vertices, can be partitioned into two disjoint non-empty vertex sets A and B, such that there is no edge between every two distinct vertices in A, and there is no edge between every two distinct vertices in B. That's the strict definition, but in, again, as Professor Ego calls it, street language, as you can see, this is an example of bipartite graph where you have two sets of vertices as highlighted, A and B. As you can see, every vertex is in A is, they cannot be connected to any other vertex in A. So all vertices in A are disconnected from each other. They're not adjacent to each other whatsoever. Same thing goes with B. And since we have these two sets, and we can call them bipartite. Now, a complete bipartite is a graph is called complete bipartite if it is bipartite and two distinct vertices are adjacent if and only if they are distinct vertex set. So that means, in other terms, is, again, remember the A and the B. So every vertex in set A is connected to every set uh, in, in set B. As you can see, like, this is set A, the one above, which is 5, 10, 15. Each one of them is connected to every member of set B. That's what we call a complete bipartite. Now, if we have a complete bipartite, but set A, oh, does everyone see the edges? Yes. No, because Professor was saying that he was not able to see the edges. Professor Assam. Um, oh, Professor might be an issue again. Blackboard sometimes does this, even though I make sure this is a PDF. But again, sometimes it does this. So I apologize, Professor Assam. We call a graph a star if if either A or B are a singleton. That means the set only has one element. So here are the questions that I'll be trying to answer in this presentation, and I answered in the paper. For what values of n, so what numbers, is ZGN complete bipartite? I'll try to describe the connectedness of ZGN, describing the diameter of ZGN, and describing the girth. We'll get to the diameter and the girth later on once we get to that section. So before this, there's a very important result in graph theory that I need to continue with a lot of the proofs. A graph cannot be bipartite if and only if there is an odd cycle in the graph. These two statements are equivalent. That means if a graph is bipartite, it does not have an odd cycle. If it has an odd cycle, then it cannot be bipartite. The opposite is equal. If it's not bipartite, then it has to have an odd cycle. If it doesn't have an odd cycle, then it's not bipartite. But I think this excludes singletons, which is graphs with only one point. So let's start with prime number decomposition. Remember when I told you, if you noticed, the relationship between the zero divisors and how you can, divide these numbers? Well, that comes in very handy. In a sense, for every integer, we can decompose it to a set of primes that are multiplied to each other. So, and have some power. So, for example, take 12. Take 36. Sorry, 36 is 2 squared plus 3 squared. 45 is 3 squared plus 5. If you take any number, if you take any number, then it has a prime number decomposition, including prime numbers themselves, because they equal to themselves. Now, also, if a, b equals to some multiple of n, the prime decomposition of n is partitioned into prime decomposition of a and b. This is a fancy way of saying that, as we see over here, we have 36. Its prime decomposition. So what we say is that the multiple of a and b can be divided by n due to the fact that each one of them has the primes, at least one of the primes that make n, and the multiple of 2 has these primes and some more. As you can see over the case over here for 36, we had a 3 extra, which it became the multiple of n. Now let's go for the first case. What if we have n equals to p being a prime? Then the set of vertices is empty. Why is that? Because as I said earlier, prime numbers don't have zero divisors. By definition, they simply cannot. Therefore, the set of their zero divisors is an empty set. This is how we denote an empty set. And let's go for case 2. N equals to p to the power of m, p being any prime to the power of m, where m is greater than 1. This is one of the lengthiest case. I promise the others aren't lengthy. So the result we get is that it's complete bipartite if and only if n is equal to 8 or n equals to 9. And it's not complete bipartite otherwise. The way we did this is, well, we basically graphed 8 and 9, and we saw that they are complete bipartite. And we said, okay, what about the other cases? What if, p is greater than 3? Or what if, 2 to the power of m, but m is greater than 3? Or 3 to the power of m, but m is greater than 2. So we start with the first one, which is 2 equals to 2 to the power of m being greater than or equal to 4. So it's m, 2 to the power of 4, 2 to the power of 5, and so on. Well, we construct an odd cycle. Remember what I said about odd cycles? If there's an odd cycle, then it cannot be a bipartite. If it's not a bipartite, then it cannot be a complete bipartite. And that is easily done. We take the 4, and then we know it's adjacent to 3 times 2 to the power of m minus 2, which is adjacent to 2 to the power of m minus 1, which is then again adjacent to 4. So now we have what we call an odd cycle, a cycle with an odd length. And this is actually a cycle with length 3. So we show that no matter what m is, as long as it's greater than 3, then 2 to the power of m cannot be complete bipartite. I'll go for the second case. N equals 3 to the power of m, where m is greater than 2, or m is equal to or greater than 3. So that's 3 to the power of 3, 3 to the power of 4, and so on. And again, we use a similar method. We construct an odd cycle. We prove that an odd cycle exists, and therefore, it's not complete bipartite. In this case, it's 3 adjacent to 2 to the power of 3m minus 1, which is adjacent to 3m minus 1, which is adjacent to 3. And which, by the way, this is the last graph. That's the graph of it, because 3 to the power of 3 is 27. So just if you're wondering, if you want a visualization of an odd cycle, here it is. And finally, what if prime is greater than 3? And again, m is greater than 1. So we take the prime is adjacent to 2 times prime to m minus 1 minus prime to the power of m minus 1, which is again adjacent to the prime, and therefore we have an odd cycle, and it cannot be complete bipartite. Now, case 3. What if we have a multiple of at least 3 primes, 3 distinct primes, that is, and each one has a power equal to or greater than 1? It cannot be complete bipartite. And again, same method of usage, we prove the existence of an odd cycle. So for example, let's take P1, P2, P3, 3 distinct primes. There will be in Vn. And let's take n and divide it by P1. N divided by P1 is in Vn, and that's the case with P2 and P3 as well. Now, n divided by P1 is adjacent to n divided by P2, which is adjacent in term with n divided by P3, which again goes back to n over P1. That's an odd cycle. So an example is ZG30. Again, as you see the graph, it has an odd cycle of 15, which is 30 divided by 2, 10, which is 30 divided by 3, 6, which is 30 divided by 5, and back to 15. I don't know if you can see it in the graph, but here it is. It actually has multiple odd cycles, but that, we just have to prove the existence of at least one odd cycle. Now, case 4, n equals to two distinct primes with powers m1 and m2. However, m1 without loss of generality is greater than 1, so it can be 2, 3, 4, and so on, while m2 can be 1, 2, 3, and so on. So it has to be greater than or equal to 1, not necessarily greater than 1, not strictly. Again, it cannot be a complete bipartite, but in this case, as you can see, I showed a case where a case where it doesn't have an odd cycle. So we have to look another way. So in this case, we have to go back to the definition of bipartite, and we have two sets. We call them A and B, if you remember. So let's, since it's arbitrary, let's take P1, and we know it's in Vn, and we put it in A, right? Then P1 to the power of m minus 1 times P2 to the power of m2 has to be in the other set. Because if you take P1 times this number, then you get n. Therefore, they cannot be both in the same subset. So the other number has to be in the other subset. Now, also, we realized that P1 times P2 P1 times P2 are not 0 mod n. They're less than n. So they cannot be adjacent. P1 and P2 cannot be adjacent. Therefore, we put P2 in A. However, we realize, if this is true, then P2 times the number I showed you first should get you n or a multiple of n. But that is not the case. If you take P2 and multiply it by P1 to the power of m minus 1, m1 minus 1 times P2 to the power of m2, we still don't get a multiple of n. And therefore, we have a contradiction. And we know that it cannot be complete bipartite. But we still have to show... Oh, I apologize. Yes. And this is the final case, which is a case of interest to me. Case 5, n equals to P1 times P2. So it's the multiple of two distinct primes with no power greater than 1. Exactly, just 2 times 3 or 3 times 5, and so on. The proof is very simple. Again, we construct A to be members of Vn that cannot be divided by P2. So they're multiples of P1. And we construct B to be members of Vn that cannot be divided by P1, which means there are multiples of P2. Their union is all set of vertices, and their intersection, that means the intersection of two sets, that means what the elements they have in common is a null set. They don't have, there's no element in between them. Then we realize that in this case, since A, all A and A are some multiple of P1, and all B and B are some multiple of P2, then all A and all B and B are adjacent. There's an edge between them. Thus, it suffices the conditions for it to be a complete bipartite. And again, here's an example of 13 times 3, both prime numbers, and as you can see, they're complete bipartite. Okay, so this answers our question. What values of n is ZGN complete bipartite? We now know that ZGN is complete bipartite if and only if n is equal to 9, n equals to 8, or n equals to P1 times P2, where they are distinct primes. So let's get to the other thing that we have to describe, which is connectedness and diameter of ZGN. We say a graph is connected if there exists a path between every two distinct vertices. That means, if you take any graph, choose any two vertices, there will always exist a path. Therefore, a graph is connected. We say a graph is completely connected if, and I should write if and only if, every two vertices are adjacent. So if you choose any two vertices in the graph, you will always have, there will always be adjacent. There will always be one edge between them. A distance between two vertices, denoted, d of v1, v2, is the shortest path between them. As I showed you earlier, sometimes two vertices might have more than one path. So the distance between them is the shortest path, or at least the path with the lowest length. The diameter of a graph is the biggest distance between all vertices. So if you bring a graph and you take the distance between all two possible pairs of vertices, and you list all of these distances, then the diameter would be the largest distance between them. So let's again go into cases. The case here being it's completely connected for n equals to p squared, where p is not equal to 2. The reason I excluded 2 is because 2 squared is 4, and 4 only has 2 as a zero divisor. Therefore, it's a singleton or simpleton graph. It will only have graph with one vertex, therefore no edges. So if it's not equal to 2, then p squared will always be completely connected. And why is that the case? Let's look. So let P1 and P2 divide n. So n, within its prime decomposition, will have P1 and P2. And, arbitrarily, let's say P2, because they're distinct, therefore they're not equal, we choose P2 to be the greater one. Then we see that P1 times 2 to the 2 times P1. I apologize. This is a proof by contradiction. That means we assume that first the n is a prime decomposition of multiple primes, not a single one. And we took some 2 arbitrary primes and continue as possible. Continue as such. So we take P1 and the double of P1, 2 times P1, which are in Vn. Both are in Vn. Are in Vn, and they're in Vn, and there is no edge between them. Now that I proved that there exists 2 vertices with no edge between them, it cannot be completely connected. Let's go. So we excluded that, and if it is completely connected, we excluded that the case in which n is a product of multiple primes. So it has to be a product of one prime to to some power. So let's see what power, if it is completely connected, would that be. So we chose let n equal to p squared, and p is not equal to 2, as I said, again, for obvious reasons. And x, y are in Vn. Vn exists, and there are 2 elements x, y. Then p has to divide x, and y has to, and also has to divide y. Well, that means that x and y both are some multiples of p. And therefore, for whatever, since they're multiples of p, whatever x, y you choose in Vn, they're always connected. They're always adjacent, because their multiple will be some multiple of p squared. Now, we saw this for p squared. Now, what if it's greater than squared? What if it's cubed to the power of 4 and so on? In this case, again, we take p and 2p. They are in Vn, but they're not adjacent, because their product will be equal to 2p squared, which is 2p squared, which is less than, which is not, which cannot divide n, or is not divisible by n. Sorry, it's not divisible by n. Finally, now you're probably wondering, since I excluded 2 over here, what if it is 2? So we take n to be equal to 2 to the power of m, where m is greater than 2. So it can be 3, 4, 6, and so on. And we take 2 and 6. 2 and 6 are always in Vn. They're always less than, starting with, for 2 to the power of 3 is 8. So 2 and 6 are part of, are always in the n being either 8, 16, 32, or whatever. And but their multiple will never be 0 mod n in the case of 2 to the power of m. So we realize that it's completely connected only if n is equal to, if and only if n is equal to p squared and p is not equal to 2. And now I'll show that it is connected and has a diameter of less than 3. Now, as I said, remember what a diameter is. It's the shortest, it's the greatest distance in a graph. So assume that the cardinality of Vn is greater than 1. Cardinality means the size, or the amount of elements in the set. is greater than 1. So again, we're assuming that the graph is not a simpleton. The graph should at least have 2 vertices. Let xy be in Vn. Let's choose any x and y in Vn such that x is not equal to y. Now, if they are adjacent, we are done, and it has, it has a distance of 1. However, if they're not adjacent, by definition, there should exist a w and a z in Vn such that x is adjacent to w and z is adjacent to y. If y and if w and y are equal, then we have a distance of 2. If if y and z are equal, then end of story. X goes to z, goes to y. That there's the path, and it has 2. Now, if w is not equal to z, if w is not equal to z, but they're adjacent, then again we have a path with a length of 3, so the distance is 3. But if they are not adjacent, we choose some h to be w times z mod n. Now w times z does, if you multiply it by either x or y, will always give you a multiple of n. Now this is a small this is a small a small thing in discrete mathematics and number theory, that the same applies to its the remainder if you divide it by n. So h, let's call h is wc mod n, which means that if you divide wz by n, you get a remainder of h. The same applies. X would be congruent to h, and x would be adjacent to x would be adjacent to h, and h would be adjacent to y, and therefore we have a distance of 2. So we showed that they're always connected. If you take any 2 points, they're always connected. There are like 3 or 4 types of connections, and at most that connection or the distance between them is 3 at most. So it's anywhere between 1 to 3. Again, here's an example. If you want to just look at it and see this, I provided Z36 as an example. Here's the zero divisor graph, and you can look at it. There's, for each of these, there's an example over here. So regarding connectedness and diameter, we realize that ZGN is always connected. ZGN is completely connected if and only if n is equal to p squared, where p is not equal to 2. And the diameter is always less than or equal to 3. So it's 1, 2, or 3. Now we go to girth. So what a girth is, the girth of a graph G, denoted by this nice function, so grg, is the length of the shortest cycle in the graph. So if we take all of the cycles in a graph, and the girth would be the shortest one of them. If a graph G has no cycle, let's say, for example, if it is a star, as I showed you, or something called a tree, then we say that the girth is equal to infinity. So again, back with cases. Let's go to case 6. N equals to 4p, where p is greater than 2. Again, this is another way of saying that p cannot be equal to 2. It's bipartite, but not complete bipartite. What this means, when we say it's bipartite, that means it cannot have an odd cycle, and therefore it has to have an even cycle. And I'll show later on that, in fact, there's always a cycle of 4, therefore the girth is 4. Now, with the proof, let set A be any element in Vn such that P does not divide A. Let B be that Vn except the elements of A. We exclude A. Let xy be in B. So let's take any 2 elements in B, and this implies that x is some multiple of P, and y is some another multiple of P. They're both multiples of P, but as I said, they have to be distinct. And A and B can only be 1, 2, 3, because if they are 4, then it becomes M. Let's assume, this is a proof by contradiction, let's assume that X and Y are adjacent. They are adjacent if and only if A is equal to B, which is equal to 2, which is a contradiction. We said they have to be distinct. Therefore, if you take any two vertices in B, they are not connected. B is the lower one. For the upper one, A, it's really a trivial case since there are all multiples of 2 that cannot be divided by P. And since they do not have P in their prime number decomposition, if you try to multiply them with each other, then you will not get 4P or a multiple of 4P. Therefore, they are disjoint. Now, I proved that it's bipartite. It cannot be a complete bipartite because we said it can only be complete bipartite. We already established when it can be complete bipartite, and 4P definitely does not meet the conditions since 4 is 2 squared. Now we have to show that there exists a cycle. And there is, in fact, one cycle that is existent for all P's, which is since P has to be at least 3, 3, 5, 7, and so on. So 8 will always be within Vn. So let's take 4, which is adjacent to P, which is adjacent to 8, which is adjacent to 2P, which is adjacent to 4. We can see an example over here of Z28, which is 4 times 7 of the case. Here's 4, and then it goes to 7, and it goes back to 8, and it goes to 14, which then goes back to 4. So there always exists a cycle of 4, and since a cycle can be at least 3, and this is bipartite and doesn't have 3, then it has a girth of 4. Case 7, let n equals to P1 to the power of M1, P2 to the power of M2, where M1 is greater than 1, P1 is greater than P2. This is similar to, I think it was case 3. So M1 has to be 2, 3, 4, and so on, while M2 can be 1, 2, 3. 1 is not excluded for M2. So we realize that girth is equal to 3 because there always exists an odd cycle. And the odd cycle in our case is P1 to the power of M1, which is adjacent to P1 times P2 to the power of M2, which is adjacent to 2 times P1 to the power of M1 minus 1 times P2 to the power of M2, which is, again, adjacent to P1 to the power of M1. And again, one case is Z18, which is 3 squared times 2. And let's take, for example, P1 to be 3, so M1 is 2. So we start with 9, which is and P1 times P2 to the power of M2, which in our case would be 6, again to 12, and 12 goes back to 9. So there always exists an odd cycle. And since an odd cycle exists, a 3 cycle exists, there's always a cycle of 3, and 3 is the minimum length of a cycle, then the girth is equal to 3. So as we've seen by cases 3, 5, 6, and 7, the girth of ZGN is either 3, 4, or infinity. And we're done. This is basically the conclusion. Just a quick recap. ZGN is complete bipartite if and only if n equals to 9, n equals to 8, or n equals to the multiple of 2 primes. ZGN is always connected. ZGN is completely connected if and only if n equals to p squared, where p is not equals to 2. The diameter of ZGN is always less than or equal to 3, and the girth of ZGN is either 3, 4, or infinity. Questions?
Great. Thank you very much, Saood. Does anybody have any question for Saood? Marwan.
Well, actually, my question at this time, probably I wanted to wait until the end to ask this question. I'm just wondering what excited Saood about this area of, other than, of course, you having Professor Ayman, uh, but were you into math before taking algebra? Have you thought that you're gonna do algebra and end up doing your senior project in this field? It's very interesting.
Well, actually, if you asked me 1 year ago, actually more than a year, if you thought that I'll be doing uh, something of this sort, I probably wouldn't have. I probably would have said no. But what happened was early last semester, as a lot of professors would know, I was going around, seeing what kind of literature of different fields of math that I could go into, and possibly do my senior thesis on. And Professor Ayman gave me this very interesting, very very interesting problem. Which at first, seeing it, the first thing that came to my mind wasn't algebra. It was more because I had taken number theory. So first thing that came to my mind, and hence why the first thing that came to my mind was prime number decomposition. And then I learned that there is an algebraic interpretation as well, was because of number theory. And me enjoying discrete math with Professor Ayman a lot. I like discrete math a lot, and I like number theory specifically. So I decided to go at it. I cracked the first bit of the question a bit, and the more I started to get into the question, I wasn't so sure if I was going to take it or not. But once I started going deeper into the question, the more I liked it. So definitely, yeah. Now in the future, I might not necessarily go into algebra. I still have a lot of fields that I want to go to, to explore. Because unfortunately, during my time in AUS, some courses were not offered, including optimization. Wanted to delve deeper in optimization, other classes. But I chose this question specifically because as I start researching, I realized that there's this deep algebraic component to it that goes into ring theory, and it's actually a special case of a paper written in 1999 of zero divisors on rings, a graph of zero divisors on rings. And Professor Ayman chose me to give me this one special case where the ring is, integers modulo n. So I realized that this is a rather beautiful, and this is why I structured my presentation on paper as such. It's a beautiful transition for people going from, let's say, discrete mathematics into abstract algebra. I can explain it to anyone who took discrete or sometimes less, which I tried to do over here. And once they took algebra, they can go, wait a second, isn't Zn then a ring? And they can start, going from there. And that transition to me was just too beautiful to pass. And so definitely, it also goes along with my ethos of trying to make math as reachable as possible. Because if I had making it a pure algebra kind of presentation, then a lot of people here would have not understood what's going on.
Okay, thank you very much, Saoud. There is a question from Dr. Sadouk in the ZGN. How big a cycle can be?
Honestly, I haven't looked into that. But if we quickly take a look, where's the presentation? It's not showing. So let's assume, for example, so if it's complete bipartite, assuming it will be, the number would be related to number of vertices in each of the set if it's complete bipartite. In cases where it's not complete bipartite, I honestly have no idea. That would be something that I have to look into and possibly study for days.
Okay, fair enough. Other questions for Saoud?
There is a question from Abdullah. Wow, I don't know who told you about this. I forgot to tell you. Wow, I'm glad that you're here, Abdullah. At what point do discrete graphs become continuous? I'm so sure what you mean by that question, because unfortunately, again, one of the classes that I did not take is graph theory. So this is actually based on my, the graph theory that I took in discrete mathematics. When do discrete? So I'm not sure. Can you explain your question further? Yeah.
It seems yes, you are wrong.
Abdullah, honestly, I'd love to hear your voice. If you can just pipe in and like say what you mean. Hypergraphs. Again, wow, Abdullah. Somehow I expected this from you. Just to let everyone know, Abdullah is doing his. I think you're still doing your bachelor's in University of California, Davis, in chemical engineering, but he has a lot of interest in physics and mathematics. I don't know, actually. I have no idea. I have to look into it. In terms of hypergraph, again, I did not delve deep into either algebra or topology or graph theory in order to answer that.
Okay. Other questions for Saood? So Saood, let me ask you a question. If I just give you a complete bipartite graph, K and M, let's say, is it does it have to be a ZGN for some Z mod N?
Oh, well, if the graph, if the vertices are zero divisors and the edges are, if you set it to the conditions that I put as first to construct the graph, then yes, it's maybe I haven't made this very clear, but it is if and only if. So it's complete bipartite if and only if it's either n is equal to 8 and equals to 9. These are the only two conditions where it's not P1 times P2. Otherwise, as I shown in other cases, that is not possible. Now, if you're talking about graphs in general, I will go slightly above, and I'll say that there could be isomorphic, definitely, possibly. Actually, I have to look into it. Like if I chose some other graph that is not ZGN, that has different set, let's say a graph of some zero divisor of some other ring, not necessarily ZN, then if I'm not wrong, in fact, when I read the paper, 1999 paper, I think if the set if the rings are isomorphic, then their graph is isomorphic as well, something along those lines.
Okay. Now, one thing, one graph in mentioned in particular was stars. Now, if the in all of your proofs for complete bipartite graph, you get to the point where it is not bipartite at all, so it is not complete bipartite. It is not by looking at only a particular cycle, which is the just the odd cycle. Now, if the graph has no cycle whatsoever, a connected graph that has no cycle whatsoever, which means it's a tree, any tree.
Yeah.
Can it be a ZGN for like what Z mod N it can be, if it can be?
I did not write this in the slides, but it would be so. To get into this, let me show you a complete bipartite graph, just to get everyone here in the picture, because this is actually a very, very important result that I didn't have the time to get into, and in fact, I left it as a question. Well, part of it. If you see, let's take A. So A over here are multiples of I apologize. It's a 13. Oh, yeah, it's 13 times 3. Yes. So where is 13? Sorry, it's 23. It's not 13 times 3. It's 23 times 13. Sorry. So, you know, for example, Z69, it's 23 times 3, right? So the amount of multiples of 3 that we have that are in VN are, as you can see over here, they're equal to 22. And the multiples of 23 in Zn are equal to 2. There is some relationship between, you know, sets A and B and the Euler function, the famous phi function, which I have observed, but I have not yet to prove it. Now, if my observation is correct, then I have not proved it strongly, but I would assume that it would only be a star in our case if we have n equals to 2 times some prime, some other prime, that is. So the reason behind that, because over here, I've suggested that B is equal to, let's say this is, this is P, let's take P1 to be 2, for example, or whatever number. Then it's it so happens to be that P minus 1 is also is related to the phi function. In fact, the phi function is related to just the size of Vn in general. So we will have, what will happen is, let's take, for example, let's take 23 times 2, that would be 46. So you take this 46 goes away, and it'll only be a star graph of 23 times 3, and so 2, 4, and so on. Infinity, then yeah, which is the case. I did show a star graph early on, which is, Z22. That's one example. Yeah. Yes. So it's 2 times prime. That's my conjecture. Again, it's a conjecture. I haven't proved it yet.
But that's for a star. But what I was asking about, like in general, if you have just any tree, it is also the Girth is still infinity. And I'm asking, in that case, what would you? Will that be a ZGN?
Well.
Mm-hmm. The star. So just the stars, you mean?
Yeah.
The tree
Seems like
is just star?
Because almost every other, I'm trying to think of another case where a cycle does not exist. Yeah, I'm having a hard time finding that.
Okay. Very good. Any other question for Saood? Okay, I guess that's it. Thank you very much, Saood. Very good job.
There is a question from Hussein Sajwani. Is it meaningful to look at more partitions of ZGN and partate, if you will? That's actually one of the recommendations that I made in the paper, that, to look if there is if we can have an n-partite kind of system. With my towing, there cannot be a complete n-partite. That's my conjecture. But are there definitely n-partites? I think so. Yes, there possibly could be. If my understanding of n-partite is, you have sets A, B, C, D, and so on, where each set is not connected. The vertices in each set is not connected, but it'd be possible. But then again, that's not something that I look deeply into it. I guess no more questions. I guess that'll be it. Just in the end, I'd like to thank everyone. I thank the professors that taught me all of these, the years that I spent in AUS. I thank you so much. Thank you, Professor Ayman, for giving me this beautiful problem and supervising. Thanks, again, professors, I thank not just only for teaching me, but even during hard times, a lot of professors were understanding and they were able to help. I'd like to thank also my parents, my siblings. They've always been a rock there for me. And also shout out to a lot of my close friends, including Khalid, who's right here. Who, again, have seen the arduous journey that I've taken to get to this point. And I couldn't be happier to get this done and to proudly say that I have presented my senior thesis. Thank you so much.
Thank you, Saood. Thanks, everyone.
Ayman, do you want anything from the committee or?
Yeah, maybe three.
Yeah.
Yes, we can hear you.